Hey folks, welcome back. In this video we're going to go over 3 worked examples to show you how to do problems involving interference by division of wavefront. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get going. Question 1a says the photoelectric effect provides evidence for the particle model of light. How does interference contradict this idea? Well, interference contradicts this idea because interference is evidence for the wave model of light, not the particle model. So this suggests that light behaves as waves, not as particles. Part B says to sketch the setup for Young's double slit experiment. Label the following on your diagram. Slit 1, which we'll call S1, slit 2, which we'll call S2, the grating spacing D, the angle to the maximum theta, distance from the slits to the screen capital D, fringe spacing delta x, first order maximum m equals 1 and 0 order maximum m equals 0. So let's start with the left hand side on our slits S1 and S2. So there's our two slits S1 and S2 there. We can then label the distance from the middle of slit S1 to the middle of slit S2 as the grating spacing D. We can then draw our screen on the right hand side and then our distance from the slits to the screen, which is capital D. And let's label some points on our screen. So we have m equals 0 that we want to label and m equals 1. And let's draw a line from the middle point between the two slits up to this point m equals 1 so that we can draw the angle to the maximum. And the distance between these two adjacent fringes is known as the fringe separation, which we're calling delta x. What we can then do is look at how the light will travel from slit S1 to the point m equals 1 and from slit S2 to the point m equals 1. And let's use dashed lines to do that. So from slit S1 to m equals 1 we have this line here, and from slit S2 to m equals 1 we have this line here. And you'll notice that the light from slit S2 has to travel further to get to m equals 1 than the light from S1 to get to m equals 1. And that means there is a difference in the distance travelled for the light, which is called the path difference. And we can mark on the path difference by drawing this line here and then showing what the path difference is, this little length. And we know that this difference is one wavelength because path difference is equal to m lambda for constructive interference. And if m is equal to 1, then we have path difference equals 1 times lambda, which is just one wavelength. So we can say that path difference to first maxima equals lambda. Part C says to use your sketch to derive an expression for fringe spacing delta x in terms of lowercase d, capital D and lambda. Well, we can say that using the two triangles from the sketch, and I'll just quickly show you those two triangles so you know what I mean. So we've got the triangle in red which has the angle theta here and the length d, and then the fringe spacing delta x. So we can use that triangle there along with trig or SOHCAHTOA. And we've also got this little green triangle that we just created due to the path difference, where we actually know the length of this side is d, the length of this side is lambda, and the little angle theta is going to be in here. So from the small triangle, we can say that sine theta is equal to opposite over hypotenuse, which is equal to lambda over d. So if the angle theta is in here, then we've got opposite over hypotenuse, where this is the right angle in this corner here. So we have opposite over hypotenuse is lambda over little d. And we can also say from the larger triangle that tan theta is equal to opposite over adjacent, which is equal to delta x over capital D. Again, looking back at the diagram, we've got the big triangle here, and if we look at opposite over adjacent from this angle theta, we've got opposite is delta x and adjacent is capital D. So we've got tan theta equals delta x over capital D. And now what we can use is something called the small angle approximation, which says that for small angles theta, sine theta is approximately equal to tan theta, and you can try this in your calculator yourself. So if you make sure your calculator is not in radians and it's in degrees mode, and you type in something like sine of 3, then that should give you a very similar value to what you get for tan of 3. So if we can make these two expressions approximately equal to each other, then that means we could write lambda over little d is equal to delta x over capital D. And to get an expression for delta x, we can multiply by the big D up to this side to get delta x equals lambda big D over little d. Part D says what effect do the following have on the fringe spacing delta x? Justify your answers. Well, we can make use of the equation that we just derived, delta x equals lambda big D over little d, to think about the effects on the different variables here. So the first part says increasing the distance between the slits in the screen, capital D. Well, from the equation, because capital D is on the numerator of the fraction here, then that means we can write that delta x is proportional to capital D. So as capital D increases, delta x also increases. So the fringe spacing increases, so the fringes observed would be further apart. We then have decreasing the grating spacing, little d. Well, again, looking at our equation here, because little d is on the denominator, that means if little d decreases, then delta x should increase because they're inversely proportional. So we could write that delta x is proportional to 1 over little d, so as little d decreases, delta x increases. Again, meaning the fringes observed should be further apart. And lastly, using light of shorter wavelength lambda, well again if we look at the equation we can see that lambda is on the numerator, so that means that delta x and lambda are directly proportional. So we could say that delta x is proportional to lambda, so as lambda decreases, that means delta x also decreases. So that means that the fringes should be seen closer together here. Question 2 says light of wavelength 695 nanometers from a laser is shone onto a double slit with a separation of 2.0 times 10 to the minus 4 meters. So you can see we've got the laser here, the double slit, and the fringes on the screen. Then says calculate the separation of the bright fringes on a screen placed 0.92 meters beyond the double slit. Well, writing down what we know from the question, we're trying to find the fringe spacing delta x. We know the wavelength lambda is 695 nanometers, which we need to rewrite in meters as 695 times 10 to the minus 9 meters. The distance between the slits in the screen, capital D, is given as 0.92 meters, and lastly the slit separation little d is given as 2.0 times 10 to the minus 4 meters. So writing down our equation for Young's double slit experiment, we have delta x equals lambda d over d. Substituting in the numbers gives 695 times 10 to the minus 9 times 0.92 divided by 2.0 times 10 to the minus 4, and if you put that into your calculator you should get an answer of 3.2 times 10 to the minus 3 meters. Lastly, question 3 says a laser is shone through a double slit with a separation of 1.0 times 10 to the minus 4 meters. Fringes are produced on a screen 2.0 meters away as shown below. Now these black rectangles represent our fringes, and you can see we've got a measurement of 38.1 millimeters across multiple fringes. It then says calculate the wavelength of the laser. Well, writing down what we know from the question, we're trying to find the wavelength lambda. The fringe separation delta x is not just going to be given by this 38.1 millimeters, because remember we want the distance between two adjacent fringes, not the distance from this point to this point. So what we need to do here, remember, is not just count the number of fringes, but count the number of gaps between the fringes. So if we go from here, which is between two fringes, to this point here between another two fringes, then that would be one gap. Then you can see from here to here, that would be another gap, and from here to here, that would be another gap. So we've got 3 gaps between adjacent fringes that fit in this distance. So we can therefore say our delta x is 38.1 times 10 to the minus 3, that's just changing the millimeters into meters, and we can divide that by 3 to get 1.27 times 10 to the minus 2 meters. Next we have capital D, which is the distance between the slits in the screen, and that is a value of 2.0 meters. And lastly, the slit separation lowercase d is equal to 1.0 times 10 to the minus 4 meters. So writing down our equation, we have delta x equals lambda d over d. Substituting in the numbers gives 1.27 times 10 to the minus 2 is equal to lambda times 2.0 divided by 1.0 times 10 to the minus 4. And then to get lambda on its own, we can get rid of this denominator first of all, so we can multiply the left hand side by 1.0 times 10 to the minus 4, and that will give us some value. And then to get lambda, you'll want to divide both sides by 2.0, and if you put that into your calculator, you should get an answer for lambda of 6.35 times 10 to the minus 7 meters. Or in other words, 635 nanometers. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.